All right, so we have this example here. You can see I've already started to set it up where I need to multiply by the conjugate. But one thing I wanted to point out here is that by direct substitution, when I plug in -3, I get 0 over 0, and specifically, I plugged in -3. So since I'm plugging in -3 and I got 0 over 0, that probably means that x plus 3 is going to be a factor that will cancel between the numerator and denominator, and that's usually a nice trick for these algebraic ones. So if I go ahead and multiply through by the conjugate up top, I have 1 minus x. Outers and inners are going to cancel, so then I really have to worry about the -2 times 2, which is -4. And then in the bottom, since I said that x plus 3 is going to cancel, I'm going to leave that as a factor and the conjugate as the other. So in the numerator, when I do 1 minus x minus 4, that becomes -x minus 3. And then I could actually factor out the negative and call it negative parentheses x plus 3. And you could see that now those cancel. So my new evaluation is the limit as x goes to -3 of, well, everything up top canceled out except for the -1. And in the bottom, I'm left with the conjugate, 1 minus x plus 2. So now by direct substitution, I have -1 in the numerator and square root of 4 plus 2, which is 2 plus 2, so I get -1/4. Here we have a more complicated example, and later on we will use some shortcuts, something referred to as L'Hopital's rule, to help simplify these. So I'm not really going to dive into this too much. So really all I'm going to take advantage of is my graphing calculator to answer this question. So I'm going to go ahead and I'm going to graph the natural log of 1 minus x minus sine x over 1 minus cosine squared. And you can see, let me zoom out, that it appears that at x equals 0, there is a vertical asymptote. And because of that, then we can actually say that the answer to this one does not exist. Goes to infinity and negative infinity without bound. Similar thing here. We could probably do these using L'Hopital's rule. Actually, you know what? The first one, 10 and 11, actually could be done similar formats. I'm going to get 0 over 0. So I'm going to try something different here. I'm going to multiply through for number 10 here. I'm going to multiply by the conjugate of the top and multiply the bottom by that as well. So when I multiply these together, I end up getting the limit as x goes to 0 of cosine squared x minus 1. And then in the bottom, I have x times cosine of x plus 1. Well, in the top, that's a Pythagorean identity. So that's really negative sine squared of x. It would be positive if it was 1 minus cosine squared. So now, using some of the properties we talked about, I could actually write this as two separate limits. The limit as x goes to 0, or maybe I'll write it as 1, and I'll write it as negative sine x over x times sine x, or maybe I'll put the negative here. So we have sine x over x and negative sine x over cosine of x plus 1. This is the identity we talked about here on this page, sine x over x. When I do the limit of that as x goes to 0, that's 1. So when I do the limit of this piece, that's 1. And then when I do the limit of this piece by direct substitution, we get 0 up top over 2. And so 1 times 0 over 2 is just 0. And again, we can verify that graphically if I graph cosine of x minus 1 over x So I'll take advantage of that. Desmos here. So cosine of x minus 1 over x, you could see that at the origin, or the graph goes through the origin. So the limit as x goes to 0 is actually 0. Same can be done for the next example. I could multiply through by the conjugate because by direct substitution I get 0 over 0, or again, I could just graph 1 minus sine x over cosine x. So I'm just going to take advantage of that. 1 minus sine x over cosine x. And we're trying to figure out what's happening at pi over 2, which, if I had to guess, is probably this point right there. 1.56 is, half pi-ish. So you can see it's approaching 0. So then the answer for this one is also 0. All right, one more type of example I'm going to leave off with here is a complex fraction. So I have number 12 here, 1 over 2 plus x minus a half over x is, as x approaching 0. So we get a half minus a half, which is 0, and over 0. So we have indeterminate form. So one option is to get rid of this complex fraction. So the expression is a fraction within a fraction. I want to get rid of that. So the least common denominator of all the little fractions, so this and this and this, is 2 times 2 plus x. That's my least common denominator. So if I multiply the top and bottom by that, let's see, let's do this first. If I multiply this by 2 times 2 plus x, well, the 2 plus x is canceled. So now we're looking at the limit as x goes to 0 of, well, if the 2 plus x cancels with that 2 plus x, I'm left with 2. All right, minus, all right, now if I distribute into this one, the 2 cancels, leaving me with 2 plus x. So we got to be careful here, 2 plus x as a quantity, so it's going to go in parentheses. And then at the bottom, I have x, or 2x, times 2 plus x. Now there's that trick showing up again. As x goes to 0, that tells me that x is probably going to cancel as a common factor. So when I distribute the negative, we end up getting 2 minus 2 minus x. So the 2 minus 2 cancels, so I get negative x over this. So now what happens is I can cancel out this x with this x. And now I could evaluate by direct substitution. If I do the limit as x goes to 0 of my new expression, which is just going to be negative 1 over 2 times 2 plus x. When I plug in 0, we get negative 1 over 2 times 2, which is negative a fourth. And there's that one. And I think that that's kind of the major concepts there. We have some trig ones. Obviously, taking advantage of a graphing calculator is helpful. Using conjugates, using the least common denominator for complex fractions, simple factoring questions, any kind of way you could simplify these ones where you get 0 over 0 is beneficial.